auxiliary audio that should give you some kind of sound. The first thing I'm going to do, can we do math now? Yes, we can. Okay, so the first thing I'm going to do, and the first thing that you're going to have to remind me to do at every session, is to start recording. So begin recording the session. Okay, today is algebra only. No, today is algebra and for the first half, and then the second half is calculus. Okay. So welcome, hello everybody. Welcome to Math1231. My name is Daniel. It is my honor and privilege to be your lecturer in algebra this term. There's some admin stuff we need to go through. What shall we talk about first? You have, Math1231 is very similar in structure to Math1131. Most of you will have done that. But just in case you need reminding or you haven't done that, there's exercises due on Maple TA every week, and you can access those through Moodle. There are the lecture notes. Now you can buy the lecture notes, but don't buy the lecture notes. Just go to Moodle and download them for free. There's a PDF which has everything you could possibly need on it. Yes, I know YouTube audio is not working. Sorry, I'm going to go ahead with this stream, and video quality is better on YouTube though. That doesn't make any kind of sense to me. I don't know why that would be. Geez. Okay. We run this course basically the same way as 1131. Yes, we do. So we've got a few things to discuss. The only thing that's going to be a little bit different in this stream is math on Twitch, please. I'll see what I can do. The only thing that's different in this stream is there'll be a weekly challenge. Now, the idea of the weekly challenge is to build up a sense of community in this course and make it just make it a bit more fun. So the challenge for this week is to take any question you like. I'm not choosy. It can be from this course. It can be from somewhere else. You take any math question you like, and you have to submit an answer as a comic. So submit your answer to me by Friday. At the end of the week, in our Friday lecture, I'll go through all the answers I have, and I will select what I consider to be the best of the responses and share them with you. So if you, it should be fun. That's the idea. Is the challenge compulsory? No. No, the challenge is not compulsory. It is fun though. So I've got a few awesome entries already. Please keep them coming. There'll be a new challenge every week, so I won't tell you what the next week's challenge is, but it should be fun too. So any question you like, submit it to me before Friday, so I have time to look at them all. Okay, will the exam be in person or online this term? I'm suspecting it's online. I think it's online. I've got no indication of a switch to fully face-to-face. In fact, I think the Vice Chancellor just sent out an email saying it's as much. We sent it to staff at least. Are there any examples of the comic we can see? Prue, no, I'm not going to corrupt you with what other people have done. I'm just going to put it out there and let you go crazy with it. Anything. I don't want you to because if I give you an example of what I think is a good response, then everyone will just kind of reflect that back to me. So I'm deliberately not giving you anything more than the challenge. We'll never have WAM again. Is the course pass-fail? My understanding is that it's not pass-fail. But again, these things are subject to change, and I don't want to promise you that just yet. I'm going to try real hard to make it a graded course so people can be rewarded for what they learn in this course. And I have to say that when I was marking the exams for another course, I was really pleased with the amount people had learned. It certainly wasn't the case that people were, just scraping by. They'd actually learned quite a bit. So I think this system works okay, but I do want you to be able to get a grade, because there's a whole lot of people out there who deserve good grades, and I'd love to be able to give it to them. Okay, all right. Where do we find the challenge? I've just told you the challenge. Miguel, this is the challenge. You make a comic strip, you send it to me by email before Friday. All right, let's do some math. So welcome, this is Math1231 Algebra. I'm just going to tell you right now, the thing that I want you to learn from this course is that you start every question with a picture. Algebra, calculus, anything. Especially algebra to me. The very soul of the subject is cemented in geometry. So if you're doing algebra and you only ever push the symbols around, then I'm afraid that's no way to live. The real soul of the subject is in the geometry of what's going on, and that's what I'm going to try and emphasize to you. So when I say, what's the first thing we do? You say, draw a picture, and I say, that's right, and we get onto it. But just so you know, that is, yes, you have been neglecting the soul of the subject, but at least you found out now. At least you found out now. So let's get onto this. Where am I? There. Okay. So, introduction to vector spaces. Do we get extra marks for drawing the comic? You get credibility from me. That's what you get, which is worth more than marks. Anyway, introduction to vector spaces. In many aspects of life, as in mathematics, we try to look for similarities in things or people that help us in categorizing things. Essentially, when you name something, when you give something a word, and your mics are muted, yes, when you give something a word, that's you attempting to tame and understand the concept. In Math1231, you were introduced to several things like R2, the vector space of two-dimensional vectors, R3, which is very similar in structure, even Rn, as well as spaces of 2 by 2 matrices or n by m matrices. You've also met things like polynomials, even functions. All these different mathematical objects. Yeah, we are moving on to the lecture content now. All these mathematical objects share an operation called addition. Now, when you open up your dictionary and you look for the addition symbol, there's nothing there. Addition symbol doesn't appear in your dictionary. What we're going to do here is kind of make our own dictionary entry. What does it mean to add? Because you add in all these different contexts, polynomials, vectors, matrices. All of these things have a symbol called add. What does add mean? What does it mean? So let's put the differences aside and look at the similarities. We'll start with R2, R2 being the kind of a sensible place. The first thing you can do in R2 is say add two vectors. And the addition of two vectors produces another vector in R2. So you add two vectors in R2, you get a vector in R2. To sum, yes, thank you, Shady, to sum. When you take two things from this vector space, from the same vector space, you produce a third item from that same vector space. Not a polynomial, not an R3 vector, not a matrix, you get an R2 vector. So the types here are important. We can also multiply any vector in R2 by a scalar, so you can stretch it if you like, and you obtain still not a polynomial, not a matrix, not a vector from R3, you get a vector from Rn. There is also a specials vector called 0, which has a very special property, that when you take any vector and you add 0, you get that same vector back again. 0 is special, very special. And here's just a little picture to get things going. You take some vector x, you understand, here it's just stuff in R2, but you have some x, and there's some things you can do with x. You can stretch it, and look, 2x. 2x is here in R2. This is our plane R2. And when you multiply x by 2, you get something in R2. When you add two vectors from R2, you get another thing in R2. The idea is that this add operation has a certain type to it, where you take in two objects of the same type and you get a third object of that type. There are a lot of incidental facts about vectors which you just take for granted. Basically, it doesn't matter if you add x and y, it's the same as adding y and x. You can be real lazy about saying x plus y, because that means exactly the same thing about y plus x. Or x plus y with brackets around it, plus a third item z. That's the same as x plus the sum of y and z. In fact, sometimes you just omit the brackets altogether and you say that's x plus y plus z. The brackets don't matter. You can add that stuff together any way you like. And you get the same result, and so on. Now let's move on to R3. R3 has almost identical structure. The set R3 or any Rn for n not infinity share these basic properties. So does a set of polynomials of degree less than or equal to n. I like to be really explicit about what the zero vector is when you talk about zero in a vector space. The zero vector in the space of polynomials looks different to the zero vector from the space R2. In the space R2, so you would say 0, 0 is the zero vector from R2. But here, this thing is equal to the zero vector, so I might put it over here, equals 0 from the space. It's the zero. We denote the space of polynomials. P of degree n with real coefficients. So it looks like that. You could also talk about the set of 2 by 2 matrices. They also obey the rules of addition. You can scalar multiply matrices. And the zero, what does the zero look like in the space of matrices? Looks like a box of zeros. In this case of 2 by 2 matrices, it's just a box of zeros. That's equal to the zero. Maybe I'll even put in brackets the zero in the space of matrices, 2 by 2 with real coefficients. All these sets, all these things that you've encountered so far, share the same basic properties of addition and scalar multiplication. And these are examples of what we will come to know more generally as a vector space. So far, so good? Yep, cool. Alrighty, do let me know in chat if things are going badly. Awesome. Notes are on Moodle? Yes, they are. Okay, so let's get back here. Okay, so let's move on. If you open up the dictionary and you look at the word, you look for vector space, you'll find there's nothing there. We're going to provide a definition of what it means to be a vector space and thereby provide a definition of what it means to add, what it means to scalar multiply things, what it means to be zero even. So here is our definition of vector space. A vector space, we're going to talk about vector spaces over the real numbers. So you take a field, but we're just going to take the real numbers. If you see the word field, I want you to think real numbers. So say some field. Here we're just going to use real numbers as field, although there's some other more freaky things that we won't cover in this course. Let's not confuse the issue. We're just going to talk about real numbers. You take a set of real numbers and you can build it into a vector space by adding structure. So a vector space over the real numbers is a set of objects. The objects are called vectors. We've encountered some instances of vectors already, for which addition and multiplication of a scalar, that is a real number, are defined and obey the following rules. First one, closure under addition. We've kind of encountered this already. If you take two elements, u and v, from our vector space, if v is too abstract for you, just think about v is equal to r2. Just think about r2 if things are too weird for you. Take two elements of your vector space, your favorite vector space if you like. If you add those two vectors, then what you get is still in that same vector space. That's that type issue we were talking about before. You take two vectors in R2, you mush them together through addition, you get a vector in R2. You don't get a polynomial, you don't get a vector from R3, you don't get a matrix, you get a vector from R2. And if you come up to me and say, Daniel, look at my nice addition, and it doesn't behave in this way, then I say that addition doesn't deserve to be called addition. Addition is supposed to work like this, where you take two elements of the same type and you get an element of that type. And if you're doing anything different, then that doesn't deserve the plus symbol, because everyone in the world takes plus to mean this. If for those of you doing computer science, which I believe is a fair number of you, any binary function thus, we had any binary function called plus with domain this and range that can be called plus. So, well, there's a little bit more to it, but anyone has a link to these notes in Moodle, Sam, in Moodle under the algebra lecture notes section. There's all the notes for this course. I've uploaded them. There we go. Thank you, Mary. What am I trying to say here? Yeah, those of you who are inclined towards computer science might like to think of plus as an operation which takes two inputs and produces an output, and all those three things have the same type. That's what this definition is trying to say. Okay, there's a little bit more to addition, like this one. You take three vectors and you add them all together. And essentially, this is saying it doesn't matter in the order in which you add these things. You can do u plus v first, and then add w, or you can do u and then you can do v plus w first and then add u to that. It doesn't matter. You'll get the same thing. You can essentially bracket things any way you like. And so, this is a lot of symbols. Typically, when presented with an equation, people half the people who are watching tend to lose half your audience every time. What is the meaning of all these symbols? It's you can bracket. Can. That's what this axiom means. You can bracket these two and do that first, or you can bracket these two and do that first. You can bracket them any way you like. And there is some clarification like that. You can't do brackets like that. No. You can't do silly brackets like that, but you can bracket and do these things first, or bracket these things almost anyway. I'll say any sensible. There you go. Because I know I'm going to see some crazy brackets if I leave things like that. There we go. Yeah, thank you, Nicholas. Exactly. That's exactly the kind of stuff I'm trying to avoid. Commutative law of addition. In algebraic symbols, it says that if you take two elements of your space, then you can add them up any way you like. That is to say, the order doesn't matter. That's a more precise way of saying it, is the order doesn't matter. So here, I'm just going to say order. That's what that axiom means. Is the finals of this course going to be online? Yes, it will be online. Yes, it will. Existence of zero. Existence of zero. This one is one of my favorites. It says it is very different to the others. It says that zero exists. The others don't promise you anything. Nothing is promised here. It says, all these ones say that if you have something, then something is promised. Here, if you have something, something is promised. This one just says straight up, zero exists. No conditions, no ifs, no thens, zero. It's here, we have it. It's the special, and what is it? It's the special vector that has this property. So here I'm just going to summarize that one as zero exists. It's a bit strange that we have to assume zero exists. So not so much assume, but demand zero exists. These are like the laws of vector spaces, the laws of arithmetic of vectors. And one of the laws is zero is there. Damn it, we have zero. I kind of like that. I kind of like it. It's a little bit different to the others. Existence of negative. What does it mean if zero doesn't exist? That is an excellent question, Jessica. I encourage you to ponder that for a moment. What does it mean if zero doesn't exist? This is the kind of question I want, where you go to a MATH1231 party, and this is what you bring up when the table falls silent, and you turn to everyone and say, what does it mean if 0 doesn't exist? And you all have an awesome discussion about what that could possibly be. I do not wish to deny you the pleasure of having that discussion. Will you be hosting a Math1231 party? You know it. Every Friday night, once my kids go to bed, I'll be hosting a Math1231 party on Twitch. You guys can hang out there. If 0 doesn't exist, discuss if 0 exists or not. I want you to. I want you to ponder that. Send Twitch TV link, please. I can do that. Oh, there we go. Abby Raman. Hey, big shout out to Abby Raman. He's a regular. All right. Yes, that's the one. All right. Existence of negative for each u. So notice we're not promised anything. We're not just straight up promised stuff. We're told that if you have a vector in the vector space, then I promise you something. There's a condition. What time do I stream on Twitch? Whenever my children are asleep, which can possibly be quite late, like between 9:30. If it gets to 10 o'clock and my children aren't asleep, then I have a lot of trouble. 1 a.m. Twitch stream, no, I'll be dead. Anyway, so this one here, existence of negative. Now when we are promised something conditionally, if you have a vector, and we'll call it u, then I will promise you, or the axiom promises you another vector, w, which is called the negative, such that u plus w is equal to 0. So this is saying the existence of negative. Notice that what happens if u is equal to 0? That's the only vector we're guaranteed exists in this world. If you have 0, then there exists another element w, which happens to also be 0 now, such that 0 plus 0 is equal to 0. So there is such a thing as negative 0 according to the axioms, but it's exactly the same as 0. So it's somewhat unsatisfying. In what cases is the 0 vector not exist? Richard, I want you to lose sleep over this. If 0 doesn't exist, do I exist? I don't. Closure under scalar multiplication. By the way, we're doing 10 axioms here, but it will transpire that the important ones. Let me just bring them to your attention. The ones that are actually really important are the existence of 0. These are the ones that are really important. Closure under scalar multiplication and closure under addition. That was the first one. These are the ones that we really end up using quite a lot. Okay. Closure under scalar multiplication. Now this is one of those type definitions. If you have a vector, you have to have a vector for this to guarantee anything. But if you come to me and you have a vector and you have any real number, lambda, then you can combine these two things in the operation of scalar multiplication. And what it produces is a vector of the same type. That means if you take a vector from R2 and you do this thing called scalar multiplication, the result is not a matrix, it's not a vector from R3, it's not a polynomial, it's a vector of the same type. You have to have vectors of the same type. Are 1 and 6 the same? No, Ham. One is about stretching. This is the closure closed under. And this one is closed under addition. And you will find that there are objects in this world that are closed under addition but not closed under stretching. There are going to be objects in this world that are closed under stretching but not closed under addition. There are going to be objects in this world that... wait, which axiom are you on? I'm lost. Sorry, I keep going back and forth. We're still on 6. I'm just being asked if 6 is the same as 1. No troubles. Stretching into the nth dimension. Yep. This is the kind of stuff I want you to be thinking about. So 1 and 6 are they're both binary additions. Even the type is slightly different here though. So here you don't take two vectors and add them together. You take a scalar and a vector, and you stretch it. Domain means scale. So thank you. The domain here is a vector. So you take two things. This is a lambda, and this is a vector, and the product is another vector of the same type. Cool. Why is the domain? William. That's a kind of shout out to all the people who are doing like things like functional programming. They would see binary operations defined in this way. All you need to know is that plus takes, when you add things, you're adding two things of the same type, producing something of that type. And for scalar multiplication, this thing called dot, you take a real number and a vector, and you produce something of the same type as the vector. Associative law just says you take two real numbers and you can scale them. You can scale one first. You can scale first and then scale a second time, or you can take those two scalars, multiply them together, and then scale it by the vector. There's not that much to this one. It's how do I explain this one in words? Really, there's a multiplication going on here, and what it's saying is you can do the multiplication in the world of scalars over here, and then multiply by the vector, or you can multiply by the vector by one scalar and then multiply by another scalar. So you're doing the multiplication here in the world of vectors, and you get the same thing. So it doesn't matter if you scale, you do all your multiplication in the field of scalars or in the real numbers, or you do all your multiplication as these multiplications in the world of vectors. You get the same thing. Multiplication in any order, sure, Shady. That's a good way of thinking about it. Order of brackets doesn't matter, even in scalars. Yes, I like that one. Maybe not so much order, but let's say brackets. Let's just say brackets don't matter. This can be another summary. Brackets. Not eraser. Brackets. Brackets doesn't matter. That's the title of my new album. You can all download that on somewhere. How many of these rule sets haven't? Only a few more. Only 3 more. This one, to give you some indication about how often things get used. This one don't even have a name. This is just axiom 8. If you have some vector in V, then 1 times u is equal to u. This is the kind of things that happen when you try and write a dictionary definition of what it means to be a vector. You have to define everything. And I'm going to go on a little rant about this. We define 0 but not 1. Yeah. Well, 1 comes from this one here. This is from 1 from. One is from is. So we're going to assume here that you actually know what 1 means, and you have a perfect understanding of the world of scalars that you're working with. So here, when I say 1, it is from the world of scalars. And when you scale by 1, you just get that same vector back again. Bit strange, but we do actually need that as an axiom. Isn't this just an existence of 0 but for no multiplication? No. This is saying if you have something, so you actually already have to have a vector in order to make any kind of and deduce anything from this. You're not promised any vectors exist except for 0. So if you have a vector, it may or may not be 0. Then you can multiply it by 1 and get that same vector. That's what the axiom is saying. What does closed under mean? Closed under means is the same type. So let's put that one down. Closed closed under means. Closed under, maybe I'll say closed under operation. It's because we're talking about two operations here, closed under operation. Means it has the same type after. Oh, the result of that operation has the same type as the inputs. There. That's a better way of saying it. Yeah, that's what I mean. Cool. Samuel says it's not the same as 6. All 6 says is that if you multiply a vector in a vector space, then it's a vector from the same space. Yeah, that's exactly what it says. Multiply. Yeah, I understood that's what you meant. Charlie, I see what you mean though. Like it's an object that does nothing for that particular operation. Is that about? Are we talking about? Isn't the Oh, it's like the identity for it is very much kind of like the identity, but for multiplication. But in Axiom 8, we're not promising that a vector exists. We're promising a scalar exists. I guess that's the way of thinking about it. Yeah, cool. Okay. I'm glad we're there. But in the Axiom 4, it's saying a zero vector exists. Alrighty. These two are pretty much the same thing. I'm just going to sum these two up as saying addition plus and scalar play. That's the way I think about these things. They play nice together. So if you have lambda plus mu times a vector, well, you can do these additions first, or you can scale the vector individually by lambda and by mu and then add the results. And you can do it either way. And similarly over here, if you scale the sum of two vectors, well, that's the same thing as scaling those two vectors individually by that amount and then adding them. It's these operations of scaling vectors by amounts and adding them play nice together. Basically, in scalar we can assume there is a 0 and a 1 among the vectors, right? Not a 1. You can assume there is a 1 as a scalar. So 1 exists as a scalar. I think that's the kind of equivalent axiom. Okay. I might pause for a moment and just share something with you. What we've basically done here. Let's just go back in time for a moment, because it wouldn't be one of my lectures if we didn't start off right and talk about Babylon. So what we've done here is just observe. The world of mathematics is full of these little things called facts. So these little dots here, these little dots are facts. You know a whole bunch of facts about vectors. These are kind of true things. So there's a whole lot of dots. One of these dots is Pythagoras' theorem. This here is a dot about multiplying a vector by 1, and a whole lot of these things. Actually, that one would technically be down here because I'm going somewhere with this. So in this world, true facts. These are the true facts. Thank you. Yes, I'll get there. I'll get there very soon. I just want to explain culturally where this is all coming from. These are the true facts. Now you know how to get from one of these facts to another. And in ancient Babylon, what they would do is they'd say, well, I know this thing, and using this thing, I can deduce this thing. And some days they might forget that they knew this, but they remember they knew this, and then they'd say, oh, well, using that thing, then I can prove that thing. None of these facts was more fundamental. They just go, oh, well, here's something I know, and I can use something I know to deduce something I don't know. That's pretty much how it was in the earliest times. People knew stuff about maths, and they used what they knew to deduce other stuff. Then along came the Greeks, and the Greeks said, well, wouldn't it be nice if all these things we know stem from some core group of truths? So they took some of the facts and they called them axioms. And the idea is that you can build up all of mathematics from these things at the bottom and use those things, these kind of what are called the axioms, I'll write that down there, axioms, to build up everything that is true about mathematics. So there, this one, and so the idea is that everything can be derived from the axioms. So these 10 axioms here, these 10 axioms we've just discussed, allow you to deduce a whole bunch of stuff about, or everything there is to deduce about the world of axioms. So if you're about not the world of axioms, about the world of vectors. Now, isn't that cool? Isn't that cool? Wouldn't it be nice if we could just boil the world of vectors? Isn't it nice that we can just boil the world of vectors down into this core 10 truths, if you like? Would it be nice if all of life could be done, could be kind of neatly summarized in this way? Well, actually, that can't be so. It's this kind of mathematical construction is only possible for things that are relatively simple. Also, this is, I mean, it's cute. It's very logically sound. This is not what you would Gödel's incompleteness theorem. Yes, go look that up if you want more tasty morsels. Practically speaking, the Babylonians had it right. What you end up doing when you're using mathematics in the real world is not deriving the thing you want to know. You don't. If you want to use Pythagoras' theorem, you don't start from the axioms and then build up to Pythagoras' theorem after 200 pages. No, you know Pythagoras' theorem is true, so you just use it to deduce stuff. You do not reinvent the wheel every time. We're going to get some practice in this kind of formal reasoning based on axioms, but when you go out and use vectors in your careers as engineers and so on, you'll be doing it the Babylonian way, which in my heart is the correct way of doing it. Right, back to where we were. Right, so we've just defined the laws, if you like, the laws of vector spaces. Let's keep going. You can also define vector spaces with slightly different fields, like complex numbers instead of real numbers. That's a kind of freaky thing that happens in later years. Okay. So normally we refer to R2 as a vector space, but what we really mean when we're talking about R2 is not just the space, it's not just the space of things that look like this. It's a little bit more than the vector space of things like this. So R2, I mean, strictly speaking, R2 is the set of all vectors where A and B are real numbers. That's what R2 is, the set of pairs of real numbers written in this way. When you're saying R2 is a vector space, you're going a bit further than that. You're saying, here's my set of pairs of numbers, but I'm also going to say that you're allowed to scale all this stuff by scalars. So that's scalars. Let's go. This one's the vectors. Scalars. And when you're calling it a vector space, you're saying, well, there is an operation called addition. Remember, axiom 1 says there is addition. Addition is a thing, and it gives you some kind of rules about how addition should behave. And also, scalar multiplication is a thing. Scalar multiplication exists. Addition exists. and the objects, the vectors themselves exist. So a vector space is really these four objects all together. Not only just the vectors themselves, but operations of addition and scalar mult. So when you're talking about R2 as a vector space, you are invoking these extra operations as well. For a vector space to be a vector, it has to follow all these axioms. For a set, for a set to be a vector, maybe I'll let's talk about this as a set. That's probably the best way of describing it. Here's a set, and all these four things together equals a vector space. Yeah, no, I blame myself, Richard. This is entirely my fault. I should have said set. A set of objects together with the scalars, together with an operation of addition, together with a scalar operation of scalar multiplication. These four things are what you mean when you say vector space. What's the name of the bracket operated object? It just means four things together in no particular order. This is the same bracket used for sets. It's just wouldn't the original set contain the other three conditions? No, it's just pairs of objects. You haven't defined. I mean, when you talk about it, you understand. Oh yeah, I know vector spaces. I can add things, but that's not immediately clear to you when you start talking about just pairs of numbers. You can talk about pairs of numbers without defining these operations. If you're doing it in, say, a computer program, when you just want a list of pairs, there's additional structure that gives you this defined in this way. Okay. Let's just move. I want to do an example. If we all the axioms excluding 1, 4, and 6 always true need to be tested. Charlie, if you're trying to prove something is a vector space, yes, you need to show that all 10 of those axioms are true. But the good news is that it is only rare that you get to ask to prove something is a vector space by proving all 10 axioms. Mostly what we talk about is vector spaces living inside known vector spaces. So you get a lot of those things for free. We'll get to that later. That's not for today. What we end up doing is mostly just using known vector spaces to build other vector spaces, and it's a lot easier to go about proving things that way because most of the work is done for you. So. So Charlie, to answer your question, technically you need to test all 10. In practice, and in particular in this course, that's rare, and you end up only testing those 3. So yes. Okay, let's just talk about these briefly and get on to an exercise. So the space of polynomials, this notation here is used to denote the space of polynomials of degree less than or equal to n. And really, when you talk about polynomials often messes with people's heads a bit. Normally, when you're talking about polynomials, you're concentrating on the x's. These are the interesting objects when you're talking about the space of polynomials. If we're going to write MPI, it's bold in the notes. Do we have to use the arrow above? I'm happy just to use whatever the notes use. So normally when you're talking about the space of polynomials, it's the x's that are interesting to objects to us. As a vector space, these x's mean nothing. They are just placeholders. The only purpose of having an x and an x squared is to be the only purpose of these things is to serve as placeholders for our coefficients. It's actually the coefficients that are interesting here. You've got a 3-dimensional vector. It's actually a 4-dimensional vector space because it has a constant coefficient, a b coefficient, a c coefficient, and a d coefficient. These are the things that are allowed to be free, and the role of the x's is only to serve as placeholders. So x, let's say x's here. X serves. Maybe I'll even say x0, x1, x2. x to the 0, x to the 1, x to the 2, dot, 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 r. It's the coefficients that are interesting. The x's are just there to take the place of the coefficient. Maybe e.g. as an example, I'll give you the only thing that is known to exist in this vector space by the axioms, which is 0 plus 0x plus 0x squared plus 0x cubed. This vector here exists. The x's are always going to be there. We don't really care about them. Their role is just to separate this 0 from this 0 from this 0 from this 0. That's all they're there to do. The space of polynomials has extra structure on top of it. For example, you can do things like evaluate it at x equals 1 or differentiate the polynomial. We don't care about that stuff right now. All we care about is the different this object is having 4 components, and you can add them and you can scale and multiply them. These are the only important things to us from the perspective of vectors. And you can also have matrices, but let's not do that right now. So let's finish with an example. Consider this set. Is this a vector space? They are scalars. The coefficients they are scalars, and together with the little placeholders, they become a vector from the space of polynomials. So this one, consider the set of things, pairs from R2, where y is greater than or equal to x. Now, is S a vector space? I forgot to add that to the notes. How do we determine if a number is a scalar or vector? Hopefully that becomes clear when you're doing the question. If the question doesn't make that clear to you, then the question is poorly worded. Let's talk about this set. First thing we do. What does the set look like? Glad that we're starting off right. What does this thing look like? Here's x. Here's y. Here's the line x equals y. And we're talking about the set of all possible vectors in the space where y is bigger than x. So that means this kind of region over here. This whole slice of the plane. This stuff. Is this, okay. So first we drew a picture. Whenever I see someone do a question and they start with a picture, my heart feels all warm and fuzzy inside. I know that this is going to end up just fine. Is it a vector space? Well, let's have a look at some of the axioms. Does it contain 0? That's the first thing I'd always check, because vector spaces are supposed to contain 0, and it's really easy to check. So 0 is in S because 0, 0. Now, what does S to be in S mean? To be in S means you're a vector in R2 and you satisfy this condition. I'm going to say 0 is in S because 0, 0 is an element of R2 and 0 is greater than or equal to 0. Good. Think about this. So now we're just showing that 0, this set does actually satisfy, hence S satisfies axiom 4. That's the existence of 0. Is it closed under scalar multiplication? Really, we're just probing this set now. So we'll assume that it has the same addition as scalar multiplication operations you are familiar with. And I should really have said is the S plus real numbers. It's all falling apart now because I'm rushing. Is S with the real numbers with the usual definition of addition and scalar multiplication. Is this thing a vector space? Okay, so let's just test some of the axioms. 0 is in S. Okay, so it does satisfy axiom 4. What about closure under addition? if I take two vectors from this space, you could have said 0. Yes, yes, I could have said that, but I kind of prefer writing exactly what it says in this definition. Let's just think about what it means to be closed under scalar. Oh, no, I want red. Closed under addition. Closed under addition geometrically means if you take two vectors and you add them up, you make a little parallelogram like that. And the result of that in teal is, hopefully you can see that diagonal there, that big diagonal. I'm going to make it big so you know what's going on. The result is always in the vector space. So basically, if you start with two sides of a parallelogram inside your space, the whole parallelogram is going to be inside your space. And actually, it's true that this thing is closed under addition. And maybe you can see that just geometrically. So if x and y are in S, then x equals, let's call it x1, x2, and x2 is greater than or equal to x1. Y is y1, y2, and y2 is greater than or equal to y1. So x plus y, the vectors x plus y, is equal to, well, you know how to sum these things up. That's y1, x1 plus y1, x2 plus y2. The sum of these things, now we're going to show it's in S, and that means the sum is an element of R2, no prizes for knowing that, and x2 plus y2, well, this one is greater than x1, and this one is greater than y1. Hence, S satisfies axiom 1, the closure under addition axiom. The final thing, so far it's kind of looking like a vector space. We've tested a bunch of axioms and we've shown that it seems to satisfy those axioms. Now, when you're trying to prove someone is guilty in a court of law, you need evidence, and you only ever need one piece of evidence, and that one needs to be rock solid. So what we're going to do now is shift gears a bit, because we don't need to prove, I mean, I'm just doing this stuff because I want you to see how to show things, how to prove axioms and for a set. What we actually need to do is show that it's not a vector space. And when you show something is not a vector space, what you do is you grab a vector and you show that it doesn't satisfy the axiom. But you need an actual vector here. None of this x1, x2 business. None of this choose any old element of S. You grab an actual vector, and your choice of vector is critical. I'm going to choose but 1, let's see, y has to be bigger than x, so I'm going to choose 1, 2. But 1, 2. 1, 2 is an element of S, since 1, 2 is an element of R2, and if S satisfies, I'm going to use the closure under negation 1. It's, yep, exactly. Scalar -1 incoming, exactly. Is this axiom number 5? I've forgotten. I just have to scroll back. Axiom number 5. X5. Then -1, 2 is in S. Alas, -1, -2 is in R2, but -2 is not greater than or equal to -1. So S What I want you to appreciate here is the very different strategies we used in proving these two things. For this one, for the first two, we showed that it does satisfy axiom 4 and it does satisfy axiom 1. So, and the way we did that is by taking arbitrary elements, any old element of x and x and y, with just generic properties, and showed that any old element is still in the set. The sum of any two elements is in the set. But when you're showing something disobeys the laws of the vector space, you need an actual vector. You call forth your witness and say, bring forth 1, 2. And then you interrogate 1, 2, and you say, sir, check out my 1, 2. It is an element of the set, but does not obey the law of existence of negative. It doesn't obey axiom 5. You need to be very careful of this because some vectors in this set do obey axiom 5. For example, if I chose 0, 0, or anything along this line, all those ones do obey axiom 5. So you need to be really careful about which vectors you choose, because sometimes the vectors do actually obey axiom 5. You need to choose one that doesn't. Okay. Alas. What does alas mean? It's like a fancy way of saying but. But I already said but, so I needed to use something else. Okay, that is calculus time. Are we having calculus lecture now? You are. Jaya, are you around? I haven't heard you. So do I need to stop sharing something so you can share something? Is Jaya here? Jaya, if you're here, he's here. Yay, Jaya, it's time. You are up. Do you want to turn on your microphone and let everyone know? I'm going to stop sharing my screen so you can share your screen. You think it's harder to prove than it yes, mate. Possible. Oh, Jay, yes. Okay.
Yes. Let's see. Check the audio here.
I can hear you just fine.
Yes, Daniel, you can see the screen now?
Yeah, I sure can. Looks good.
Okay. All right then.
No? Why?
Yeah, initially I had some difficulty joining in. I managed to join in, so I'm staying on.
What's going on? I have to kind of be around.
A cold call from Dan Riley.
Who's he?
Dan Riley.
Oh, yeah.
They've actually been stepped up. They're stepping up into a role above them. And for these 6 months, and they want to do the active transport team break it in half and have it.
Sure. Yeah.
And they're like, just a soft, just say we want them in why. What do you think?
That's so exciting. So it's in transport? And where in transport? And what level in transport? Like, what's going on?
Just sideways.
Fucking take it. It's great. You're working with people you like.
Well, I've been working with them. I like the question is, I actually have some pretty big opportunities here going to what I can do and how I can.
So hang on, just so I understand, it's active transport, but they just want a slightly different, they want to specialize
I
and
want to break it down into two sections.
break it into a section with you and a section with Helen.
No, break it with the other active transport person, Sarah.
Okay, the one who lives up the road. Okay, she has a nice bicycle. That's all I know about her. Apparently she could be trouble, but it can't be worse than what she got now.
Okay.
Okay.
Some of the teams she has.
Hi, students. Can you hear me okay?
Many hers.
Oh, okay.
Excellent. Thank you.
Just someone until 30 said, listen, I've actually got someone trying to punch me.
Very good.
And then ask them to-
So welcome to the first lecture in calculus. So some information here on the slide. As you have heard from Daniel, the algebra and calculus lectures are on Monday 2 to 3, calculus Friday 4 to 5 as well. On weeks 1, 3, 5, 8, and 10, Wednesday 1 to 2, we will have calculus lectures. Okay. So my name is Jaya Kumar. I'm your calculus lecturer for this term. All right. So let me give you an overview of the topics we are going to cover in this session.
I want you to go to
Now,
let
me remind you, I'm using a document camera, so I'm giving this lecture using two computers here. I'm using one computer for capturing the document camera, working out and so on, and other one to monitor your questions and so on. All right, so here are the topics we'll be looking at. First one is functions of several variables, then integration techniques, and ordinary differential equations, and Taylor series, and sequence and series, and the last topic is on averages and arc length and surface area, and so on. So basically, in the term 21231, we'll be looking at applications of calculus techniques.
How many people are watching it on YouTube?
Okay. So the first topic is on functions of several variables.
How do you watch it on YouTube?
The functions of several variables appear more often than functions of a single variable in applications of mathematics. For example, the volume of a right circular cylinder is a function of its radius and height. So for different radius and height, you get the different value for the volume. So we may write that mathematically V equals pi r squared h. So, or we can write V as a function of r and h. Well, for different values of r and h, we calculate the volume. So another example, here, let's look at the function fxy equals xy. So this function gives the area of the rectangle of dimension x and y. Right? X, so x is the length, y is the width. So you get the area of the rectangle given by the formula fxy is xy. Okay. Now, if we want to look at a three variable example, let's consider fxyz equals xyz. So that gives you volume of a rectangular solid of dimension x, y, and z. So something like this. So x, y, and z. So you calculate that volume x, y times z. So there are simple examples. So I would like to give you a practical example where you can see how that function several variables appear. So have a look at this example. I haven't given this example in the outline lecture notes. Don't worry about copying it down. I will post that example and the solution after the lecture. So set up you are asked to set up a mathematical problem for finding the dimension of a closed cylindrical tank with a fixed volume C. which has the minimum surface area. Okay, so we would like to find the optimal dimension of the cylinder with the fixed volume that gives you the minimum surface area. So let's see how we can set this problem up as a mathematical problem. Now, if you want to write a mathematical problem, we need to define variables x, y, z, and so on, and then write down equations and inequalities and conditions, and describe the problem mathematically. So the first thing is to set up the problem. Let's draw a little diagram. So we're talking about a cylinder, closed cylinder. Okay. So first we need to define. So first step we need to do is to define the variables, right? So let x equals the radius of the cylinder and inequalities and condition and describe the problem. So x equals. So the first thing is to set up the problem. Let's draw a little diagram. So we're talking about y. So a cylinder, closed cylinder. Okay. Okay. So then we would like to describe. So first we need to define the volume. So first and we need to do is to define the area, right? So in terms of the variable x and y. So the volume of the cylinder is the height times the area of the circular cross section, which is given by pi x squared y, which is given as a constant c. Yes, this exercise is not on the notes. Don't worry about that. I will post that problem and the solution after the lecture. So that is the condition we have here. The cylinder should have the fixed volume C. Now we need to calculate the surface area. The surface area of the cylinder, area S, consists of the curved surface plus the two circular ends. Plus there's two circular ends. So we describe that in terms of the variable x, y, and z. So the curved surface area is 2 pi xy, and top and bottom are pi x squared, and the 2 times y x squared. Okay, so that gives you the okay, so I need to move that. All right, should be clear now. So that gives you the surface area. Now we can describe the mathematical problem. So the mathematical problem is, so I'm moving up here. Problem is you want to minimize the surface area. That's 2 pi xy plus 2 pi x squared, subject to the condition that we have the fixed volume, pi x squared y equals c. Pi x squared y equals c. Okay, and obviously you can add the additional condition. If you like, the dimension cannot be negative. So x is bigger than or equal to 0, y is bigger than or equal to 0. Now, so the problem of this type can only be solved using differential calculus of functions of two variables. You should be able to calculate partial derivatives and so on, which we'll talk about later on. So in fact, the last term, I taught a course on optimization where the last 10 weeks, we solve a problem of this type, where every week we apply the calculus of functions of two variables or three variables or even more to solve problems like that. So problem of this type, decision-making problem that appears in data science area, engineering, commerce, and so on. So even the high variable, if the number of variables involves more than 10, we may have to use the computer. To use the computer packages, we have to first do the mathematics. So we need to apply the calculus first to solve this problem. So this gives you a motivating example why we need to study several variable calculus. Okay, so now I'm going to look at the various forms of functions and then how we can calculate the partial derivatives and so on. And also we will look at how we can sketch graphs of functions of two variables. So more generally, see, we will consider functions of the type z equals fxy. Okay, for example, fxy can be x squared minus 3xy plus y to the power 4. Or fxy can be 1 over x minus y, where x is not equal to y. So what happens here, you have input x and y, two variables, and you get the output fxy. The function gives you the output fxy. So in this case, we input x and y, you get the output x squared minus 3xy plus y to the power 4. Okay. In the simple example, the inputs are the radius and the height. The function, the b equal pi r squared h gives you the volume of the cylinder. Okay. So the next question we want to look at is how we can sketch the. Yes, we can. We will be. There is a confusion on the notation. Z is used in algebra for complex numbers as well. Yes, we will be using Z to denote the value of the function of x and y. Okay, so we want to look at some examples. So as I said before, most functions depend on more than one variable. Here are some examples here. Let's look at example one-dimensional. So one-dimensional, so dfx equals x, for example. So in one dimension, so it's the point P. So distance from the origin is x. So OP here is the distance d, which is x. So the function here, function of single variable, fx equals x in the one-dimensional case. You have seen lots of examples like this in high school calculus and so on. Now, let's look at an example two-dimensional case. So two-dimensional case, equivalent distance from the origins can be given like this. So in two-dimensional case, x and y here. So there's a point P here. So this is x, this is y. So that gives you OP squared from the right triangle as here x squared plus y squared. So OP, so that's the distance. D is square root of x squared plus y squared. Okay, so therefore we have a function of two variables here, f, x, and y in this case, square root of x squared plus y squared. Okay, so let's look at the distance from the origin in a three-dimensional case. So in a three-dimensional case, so let's sketch a little diagram here. That's x, y, z here, and so that's point P. So draw a line here. So that's perpendicular. That is x, y, z. That's the point. So that is x here. That's y. This is y, and this is 90 degrees as well. So that let me call it M, and this is N. So from this triangle, OPM, OP squared is OM squared plus PM squared. Okay. So from this triangle here, and the second triangle on the xy axis here, OM squared is ON squared plus NM squared plus PM squared. Okay, so that gives you, so ON squared is x squared plus y squared plus z squared. So in three dimensions, OP equals square root of x squared plus y squared plus z squared. So you have a function of three variables in this case. Square root of x squared plus y squared plus z squared. So that's the distance from the from the origin in a three-dimensional case. All right, so we want to look at how we can sketch graphs of function of two variables. Okay, the function of two single variable is easy, y equals fx, a graph is in R2 is a curve. All right, so function of two variables, graph is a surface in R3. Okay, so we want to look at a few examples of how we can sketch simple surfaces. And first, we want to note, generally, function of two variables represents surfaces in 3D. Okay, so the graph of the function of two variables one dimension high, that's in three-dimensional space. So, for example, so that is the surface set fxy. Okay, so the point here on the surface, x node, y node, fx node, y node gives you the height from the xy plane here. So x node, y node, that's the height there. So that gives the height of the surface above or below the xy plane. If that is positive, then the point is above the xy plane. If that is negative and below the xy plane. So that's the convention we will be using. Okay. Here's another illustration of that. So the conventional orientation is this xy plane here, x, y, z. Z is the distance above, that's plus, or below, minus the xy plane. Z value is positive, the point lies above the xy plane, or the surface will lie above the xy plane. It's negative, it's below the xy plane. Now, to understand that, we need to look at some simple example. It's not always easy to sketch surfaces of function of two several variables. So we will look at some simple example and see how we can sketch the surfaces. Okay, to sketch surfaces, we need to look at the ideas of level curves and profiles. So what's the definition of a level curve? So a level curve of a function of two variables from R to R is a curve in the xy plane defined by fxy equals constant. C is a given constant. Okay? So, and the profile is obtained from the plot of z versus y. That gives you, for example, when x equals 0, yz profile gives you the intersection of the surface with the yz plane. We can also look at the profile z versus x with y equals 0 and combine them to sketch the surface. Okay, we will look at some simple example how this can be done. First, we need to sketch level curves and then look at the yz profile, xz profile, combine them to sketch the surfaces. Okay, here's the first example. So sketch the level curve and profiles of function of two variable fxy is x squared plus y squared. Now, first you want to look at the structure of the function. It often gives you some idea how the curve would look like. So let's say equals fxy. So by looking at this equation here, fxy is x squared plus y squared. So they are sum of squares. It's always bigger than or equal to 0, right? For all xy. So that tells you z value is always will be bigger than or equal to 0. That means the surface will lie above the xy plane, in the horizontal plane, right? Because that value is always bigger than or equal to 0. Okay, now first we will sketch some level curves. So each level curve is obtained by setting z equals constant for some constant c, right? Okay, so level curves means z equals constant c. Okay, so let's look at some z values and its level curve. Okay, so z equals 0. Let's put z equals 0 first. When z equals 0, that means x squared plus y squared equals 0, which means x equals 0 and y equals 0. That's the point, right? And so z equals 1. Z equals 1, you get x squared plus y squared equals 1. So that is a circle with radius 1. And so z equals 2. So that gives you x squared plus y squared equals 2. That is root 2 squared. So that's the level curve is a circle with radius root 2. Okay? And for example, let's do one more. Z equals 4. X squared plus y squared equals 4. So that means that's 2 squared. That's also a circle with radius 2. So let's sketch the level curves here. X, Y. Oh yes, I'll let you know about the difference between the level curve and the profile. So first I'm focusing here on the level curve. We look at the next thing is to look at the profile. So level curve here with z equals 0. That's the point here. Z equals 0. So that is the point. So z equals 0. Z equals 1. X squared plus y squared equals 1. That's a circle with radius 1. That's z equals 1. And z equals 2. Z equals 2 is radius root 2 here. And there's another one. That's for so z equals 4 is radius 2. So these are the level curves. So what does it tell you here when you, in three-dimensional space, when you sketch the surface? So when z equals 0 in the xy plane, you have a point. When z equals 1, when the surface, the intersection of surface and the z equals 1 plane is a circle, 1. And similarly here, the intersection of the plane z equals 2 and the surface is a circle with radius root 2 and so on, right? Okay, now look at the yz profile and xz profile. Okay, so yz profile. So yz profile, zx equals 0. Okay, so z equals x equals 0, 0 squared plus y squared, so z equals y squared. So that gives you in the yz plane, so that is z equals y squared, it's a parabola. Okay, so that means the intersection of the surface with the yz plane where x equals 0 is a parabola. Similarly, let's look at the xz profile. And again, xz profile y equals 0. So that gives you z equals x squared plus 0. That's z equals x squared. Again, that is a parabola here. X z. Now we put together to sketch the surface. Let's see how we can sketch the surface here in three-dimensional surface. We know that by looking at the formula z equals x squared plus y squared, the surface lies above the xy plane because z value is always bigger than or equal to 0. Okay, so initially when z equals 0, the xy plane, you have a point here. And the previous calculation on the level curve, when z equals 1, the level curve x squared plus y squared is 1. That means the surface intersects with the z equals 1 plane. Here, z equals 1 above the xy plane. You have a circle with radius 1 here. When there is z equals 1. That's x, y, z. Okay, so that's z equals 1, and z equals 2, that means when the intersection of surface and the z equals 2 plane, which is parallel to the xy plane at the height 2, that have a circle with radius higher than 1, there is root 2 here. And z equals 2, that is z equals, z equals 1, z equals 2, similarly z equals 4, the radius increases here. Okay, then we know the profile, yz profile of the intersection of the surface with the yz plane, which is a parabola, so that like this. So that's how you get the surface here. Okay, this is called the paraboloid. So we put together here the level curves and the yz profile and the xz profile to sketch the 3D surface. Now let's look at another example. So let's here on your slide as well. So the xz profile gives the intersection of the surface with the xz plane, and yz profile gives the intersection of the surface with the yz plane. Okay. And then here's the Maple generated graph. Looks a little bit better than mine. So that gives you the paraboloid here in the 3D. Okay. So let me make a small change in this example and see how we can sketch it. Here's another one. Instead of looking at z equals, this example is also not in your outline lecture notes. This is actually exercise for you to try, but I'll give you a hint here how you can do it. So I now change the formula of the function to z equals f(x) square root of x squared plus y squared. And see how the surface will look like here. So again, so you can look at the structure of the function here. It's always sum square root of that. It's always non-negative. So the graph, the surface again is going to look. The surface is going to appear above the xy plane because that value is always negative, right? All right. So the level curves are again circles. So level curves means z equals constant, right? So if you look at the sum of the z values and the level curve. So again, z equals 0 mean x equals 0 and y equals 0. It's not the same. You will see the difference here when you look at the profile. And z equals 1, again, the radius is x squared, y squared is 1, which means x plus y squared is 1. It's a circle. And z equals, say, 4, and square root of x squared plus y squared equals 4. So that means x squared plus y squared, maybe 2. So that is 2. And the radius is 2 squared, that is 4. Okay, so again, double curves are here as circles as well. So level curves, the first one z equals 0 is a point, and then you have a circle and another circle. So that's z equals 0, and it is z equals 1, with radius 1. And z equals 2, radius 2, and so on. Okay? Now look at the yz profile and the xz profile. So yz profile, to find the yz profile, set x equals 0. If you set x equals 0, z equals square root of 0 plus y squared, which is square root of y squared, which means z equals absolute value of y. Okay? So that the profile here, x, y, so here, x here, yz profile, y and z, that is absolute value of y, like this. Same as xz profile. If you look at xz profile, set y equals 0, and z equals, because z equals, when you take the square root, you get z equals absolute value of y. So in this case, square root of x squared plus 0 squared, that is square root of x squared which means z equals absolute value of x. Here, that is also x and z, absolute value of x. Now you can put together to sketch the curve and the surface here. That gives you, here's the surface in the 3D, x, y, z, 0. Initially, when z equals 0, the xy plane, it is a point, and then you have the yz profile is a curve like that, and z equals 1, you have a circle, and z equals 2, you have a circle, and so on. So that gives you a cone. Okay, you take the square root, you get a right circular cone. All right, so let's look at more example. Here's another example. Now here, you are not given z explicitly given as a function of x and y, but x, y, z are related by this equation. So in this example, we have surface in R3 is described by the equation z squared equals 1 minus x squared minus y squared. Okay, so sketch some level curves and then sketch the surface in R3. Let's see how we can do this example here. Now, again, so look at the structure of the equation first. So note here, z equals 1 minus x squared minus y squared, which is 1 minus x squared plus y squared, right? So x squared is a sum of squares, so that is always bigger than or equal to 0. Okay, so we're taking away the non-negative term from 1, therefore z squared, therefore z squared should be less than or equal to 1. Okay, z squared is less than or equal to 1. If you take a square root, you get absolute value of z is less than or equal to 1, which means z lies between 1 and minus 1. Okay, so what does it tell us? That means the surface lies between the plane z equals 1 and z equals minus 1. Right? So z equals less than or equal to 1 and bigger than or equal to minus 1. Okay, the next step is to look at the level curves. Level curves. Z equals constant. C. All right, so let's give some values and sketch the level curves. So z values and the level curve. So z equals, for example, let's say z is plus or minus 1. When you put z equals plus or minus 1, you get x squared plus y squared equals 0. X squared plus y squared equals 0. So that means x equals 0 and y equals 0. Okay. Let's say z is plus or minus half. So plus or minus half, you will get, so half 1/4 equals 1 minus x squared minus y squared. So that gives you x squared plus y squared equals 3/4. So that means root 3 on 2 squared. So again, that is a circle with radius root 3 on 2. And if you check z equals 0, that gives you 0 equals 1 minus x squared minus y squared. Yeah, here, okay, that's a good question. How do you choose the z values? This is observation made first. Z must lie between minus 1 to 1 because absolute value of z is less than or equal to 1. So therefore, that's what I am choosing values from between minus 1 and 1. Okay, so when z equals 0, 1 minus x squared plus y squared is 0. So that's the circle x squared plus y squared equals 1. Okay, so what does it mean when z equals 0? The level curve x squared plus y squared equals 1 means that in the xy plane, the horizontal plane, you have a circle x squared plus y squared is 1 with radius 1. And when z equals half, and above the xy plane, the surface, the intersection of surface and the z equals half plane, we have a circle with radius root 3 and 2. Okay, so the level curves you can sketch it here. They are in a two-dimensional space. The z equals 1. You have a point here. Z equals 1. Z equals half. A circle with radius root 3 and 2. So that is z equals plus or minus half. Radius root 3 and 2, and then if z equals 0, you have x squared plus 1 equals 1. Okay, so this is plus or minus half. And now we also want to look at the yz profile and xz profile. Let's look at the yz profile. yz profile, set x equals 0 and the equation. So that gives you a z squared equals 1 minus 0 minus y squared. That's 1 minus y squared. That is z squared plus y squared equals 1. So that's a circle. This is y. That's z. That's a circle. So the intersection of the surface and the yz plane is a circle with radius 1. Yes, and similarly, you can write you can easily write equation for xz profile. Set y equals 0. Y equals 0. So that gives you substitute y equals 0 there. 1 minus x squared minus 0. So z squared equals 1 minus x squared again. That's a circle. X squared plus z squared equals 1. You have a circle here. That is x. That is z. That's origin. So the intersection of the surface with the xz plane is a circle. Now we put together the level curve and this yz profile to sketch the 3D surface. Okay, 3D surface. Here, so let's see, we can see, can you see that? Yes. Okay. X, Y, Z. So we know that the surface lies between z equals 1 plane and z equals minus 1 plane. So, because that's what we first observe here. And level curve gives you that z equals 0, in the xy plane you have a circle. Circle. And we know that the yz profile is also a circle. yz profile is also a circle. And when z is plus or minus half, z equals half, you have a circle with radius root 3 and 2, like this, and here as well, plus half and minus half. When z equals 1, when the surface, the intersection of surface and the z equals 1 plane, you have a point. That point here and that point here. This is a unit sphere. Okay, the surface is a unit sphere. So that's 1, that's minus 1. So that's origin here. Maybe I will post a slightly better sketch than this one later on when I upload the answers tomorrow. Okay, so let's do one more example before we move on to the partial derivatives and so on. let's look at this example. Again, this one is an implicitly defined function of two variables. We don't have the explicit formula z equals function of xy. So the profile gives you the cross-section of the surface with the yz plane. Okay, yes, you're right. All right, have a look at this third example. X squared plus y squared minus z squared equals 1. A slight change in the formula here. Again, you note here that it's not given as defined explicitly as a function of two variables. Well, we have looked at many examples of sketching level curves. For example, level curve for z equals 0. We'll substitute z equals 0 here. That's x squared plus y squared is 1. That's a circle with radius 1, right? The level curve for z is plus or minus 1. You substitute plus or minus 1 here, and x squared plus y squared is 1 plus 1 is 2. Therefore, the circle with radius square root of 2. Okay, and put some other values. So z is plus or minus 2, and x squared plus y squared, that is 2 squared. 4 plus 1, 5. The radius is square root of 5. Okay, I think you in that I have given you a sketch in the outline notes. Let's look at that. Here, so the level curves are here. Z equals 0. It's a radius 1. Z is plus or minus 1. Radius root 2, and so on. So these are the level curves, circle, concentric circles here. Now let's look at the yz profile and xz profile here. I'm just going to go back to the previous slide here, and the yz profile. Let's look at the yz profile and see what happens there. So yz profile in zx equals 0. So in this equation, zx equals 0. So that gives you y squared minus z squared equals 1. Y squared minus z squared equals 1, which is a that is y z 0, which is a hyperbola. Something like that. So that's 1, that's minus 1. That's minus 1 and 1. So that is the curve in the yz profile. So the intersection of the surface and the yz plane is a hyperbola like that. All right. So similarly for the xz profile as well. When you put y equals 0, you get x squared minus z squared is 1. In this case, yz profile and xz profile are similar here. All right. So we can put together to sketch this surface. So we have the level curve here. Z equals 0, the level curve is a circle with radius 1. That means in the xy plane, you have a circle with radius 1 like that here. Okay? And Z equals plus or minus 1, the level curve is a circle with radius root 2. That means the intersection of the surface and the Z equals plus 1 and minus 1 plane, you have a circle with radius root 2 be higher than that. So that's something like that here. Plus 2 and the radius root 2. So this one is radius root 2, this is radius 1. Okay? So when Z equals plus or minus 2, the level curve is root 5. That's the circle with radius square root of 5. So the Z equals 2, that the plane is above the xy plane. So that's here. And it's a circle, and here is also a circle. We put together to sketch the graph. That's the graph you get. This is actually the maple plot of the surface hyperbola. So this is how you sketch the surfaces for simple function of two variables and so on. It will be challenging to sketch complicated function of two variable sketch by hand. For example, I think I have given on the last slide, you will see the maple plot of the surfaces of complicated functions, right? So let me recap on the on the level curves and the surfaces. Have a look at this picture here. So level curve can be obtained by intersecting the graph of f with the horizontal plane, z equals c, and then projecting this intersection onto the xy plane. So this is a 3D. You can also interpret like this. So if you look at the surface like this, that surface is given by the formula 100 minus x squared minus y squared, right? So that's the surface here. Now, if you look at the plane z equals 75, that's the plane z equals 75 there. Okay? So when you put z equals 75 there, you get x squared plus y squared is 25. So when you intersect this z equals 75 plane on this surface, you see that circle there with radius 75. Okay, radius 75. So when you project it in the xy plane, you get the level curves there. Okay, this is one way of looking at the level curves and so on. In fact, the level curves have practical applications as well. So here is an example. In the air pressure charts like the ones below. So the air pressure, these are the level curves described by the pressure which is constant along those curves. Here's another example of level curve topographical maps, which for describing the mountainous region. So if you look at the level curve here, if you walk along in this mountainous region on this path, you stay at the same height because that value is constant, right? So they are used. The level curves are used in topographical maps of mountainous region and so on as well. So that has a practical application. All right, so that is about sketching sketching surfaces. We need to look at partial differentiation. I would like to start today, the last 10 minutes, the idea of partial differentiation. So I would like to start with this today. You already have 2 hours there. I will start the partial differentiation on Wednesday. Okay, yes. So I'm going to start with this, and the stream will stop in 5 minutes as well. We will start fresh about the partial differentiation idea on Wednesday, 1 o'clock, I think. Yes. All right. Thank you very much. Hope you can join me on Wednesday.